Today we will start our trip into polynomials. Let's first stop at imaginary numbers. This is a topic I love. I love imaginary numbers. It's really interesting. And I don't like the terms imaginary versus real numbers. Implies that imaginary numbers are, well, imaginary. But in many senses they're just as real numbers. They're vital for all sorts of science topics. Quantum mechanics you can't do without. And we'll be making two incursions into imaginary numbers in our Precalculus course. The first place it shows up is in polynomials of degree 2. We'll talk about that in a bit. Say you had x squared minus 4 was your equation. You may recognize x squared as a parabola, and indeed it is. And where does this equal 0? Soon you'll learn to recognize this quickly. This is a perfect square. It factors into x plus 2 and x minus 2. We find where these zeros are. So we're just sort of describing our parabola. We could just put numbers in to get it, what it looks like. But we can also find its zeros by setting the equation y equal to 0 and then getting these 2 points, plus 2, minus 2. Well, if you push the parabola up and you cross the axis, those 2 zeros disappear. There are no more real zeros. If I was to graph x squared plus 4 equals y, what's the equation now? That's a parabola that's up here. When x equals 0, y equals 4. It's way up here at 4. So it looks like it has no zeros. These are the roots of the equation. It looks like this one has no roots. It doesn't cross here. But there is a set of numbers to get out of this. And I'm sort of drawing this going in and out of the screen. These are the imaginary numbers. You can imagine as a third axis coming out at you here. And this thing does have imaginary roots. It does indeed factor into, and we're never going to, I don't think we're ever going to do it this way. There's no number we can put in here to get this to equal to 0. This is going to be 4. We want a number square that's going to be less than 4. Any squared number is going to be positive except for imaginary numbers. And imaginary numbers is just represented by I, the imaginary part, which is the square root of minus 1. You can't take the square root of minus 1 in real numbers, but you can in imaginary. And it's this thing called I. We just sort of define it. And now we have solutions to this. You can multiply this out. Remember FOIL. This is a little tool we use to remember how to multiply these. We multiply the first 2 out, x squared. Could have done that up here and got the original equation back. Outer, x times minus 2i. Minus 2, you just treat I sort of as if it was a variable. It comes along. Inner is a plus 2ix. And the last 2 is plus 2i times minus 2i. Okay, this is plus 2ix minus 2ix. These two cancel. You're left with x squared equals, let's see what's left, minus 2 times 2 is 4, I squared. I squared is just I times I, which is square root of minus 1 squared. Square and square root are inverse operations. I'll give you back the original thing. So I squared is minus 1. So this is, oops, I meant to write a plus here. This is our equation as we're multiplying it out. So it becomes x squared minus 4, and I squared is minus 1. So the two minus signs canceling of x squared plus 4. Imaginary numbers. So when you get imaginary numbers, you don't get a real view of what they're actually doing in the parabola, but there's sort of this invisible imaginary axis that comes out of here. Sort of the upside down of math. There's some hidden axis. And let's clear this out. And we often have real numbers mixed in with imaginary numbers. And we call these complex numbers. Another scary term. They're not all that complex. And we have the imaginary plane. This will become very useful when we talk about the unit circle and things. Typically represent the real numbers out this way, and the imaginary numbers out this way. So we have 2. Oh, wait. Let's reverse that. Real numbers come out here. Send the imaginary numbers up here. It really doesn't matter. It's up to you. 2 plus 2i. I have to remember to check what your book does. Either way, you have a real axis and imaginary axis. Here's the point 2 plus 2i. It looks like 2 plus 2, but you're really just plotting one point. A complex number is has 2 dimensions. Okay, you could do 2 minus 2i, etc. There's all different kinds of things you can plot these points here. You can add complex numbers. We've already done that. 2 plus 2i plus 3 minus I. You just add the real parts. 2 plus 3, I believe, is 5. 2i minus I, left with 1i, 5 plus I. So you can add these things together. You can multiply them together. This is as complicated as we get. You can divide them too, but there you get into complex conjugates, which are cool in themselves, but we'll save those for another time. Alright, simple, same thing here. You use sort of FOIL as if this was a quadratic equation. 2 times 4 is 8. First, outer, 2 times I is 2i plus 2i. The inner, 2i times 4 plus 8i. And then you have 2i times I plus 2i squared. The neat thing about these is all the squared terms end up simplifying to something. Just a little more to say on this. So this ends up being I squared equals minus 1. So this ends up being 8 plus 10i. 2 times minus 1 is minus 2. So this is 6 plus 10i. Please watch the Vi Hard video. I'll keep this short just so you have extra time to watch that. It's really wonderful. And how these things move around. They're not ordered. They're not less than. They're ordered among themselves, but they're not ordered compared to the real numbers. It's a really neat thing. The last thing I want to say is notice if you take I squared, remember that was minus 1, so I cubed equals minus 1 times square root of minus 1. It's just minus I. And I to the 4th equals minus I times I. I squared is minus 1. This ends up being back to 1. So these things cycle between I, minus 1, minus I, 1. And if you ever have I to the 4th, you can take that out of an expression. So if I had I to the 5th, that equals I to the 4th times I. And I to the 4th is 1, so this is just I. So you can very easily raise these things to gigantic powers. Just take chunks of 4 out. And that's all there is to imaginary numbers. They are the invisible axis that exists in many dimensions. And they will show up prominently in this section on quadratics. And they will show up again when we put exponentials together with sine and cosine. Do weird things like this, which you'll soon get to know and love. Okay, that's it.